Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics. Today we are going to see about the oscillators and amplifiers, in which the sine wave generator, the types of sine wave generator, RC phase shift oscillator and Wien bridge oscillator, and next triangular wave generator. So, this is the block diagram of sine wave oscillator. So, what is an oscillator first? Oscillator without any external input signal, it is going to produce an output signal, in which an amplifier is used and a feedback circuit is used. Here in this circuit diagram, from the amplifier, some part of the output is fed back to the input of the amplifier through a feedback circuit, and this amplifier may be an inverting amplifier and a non-inverting amplifier. If a non-inverting amplifier is used, then the phase difference between the input and output of the amplifier is in phase, that is 0 degree, and if an inverting amplifier is used, then this feedback circuit must produce the phase shift, so that the total phase shift in the loop must be 0 or 360 degree or integral multiple of 2 pi. And this is one of the Barkhausen criteria which should be satisfied by this oscillator, by any of the oscillator. So, how the oscillator will produce an output without any input signal? So, initially the output of the oscillator is by the noise. From the noise it produces some output, and this output signal must be regenerated for the first cycle, and for the second cycle it has to be increased, and for the third cycle also it has to be increased, and so on. If it is increased, and the output of the oscillator will get sustained at one point, for which we have to follow, the oscillator has to follow two conditions, and these two conditions are called Barkhausen criteria. In this block diagram of an oscillator, this A is the gain of the amplifier, and for the feedback circuit has the gain beta. So, what is the Barkhausen criteria? A beta must be equal to 1, and that is the magnitude of the product of the gain of amplifier and the feedback circuit must be equal to 1, and the phase of A beta must be equal to 0 or 360 degree or multiple of 2 pi. These are the two conditions the oscillator should satisfy, and this is said to be Barkhausen criteria. Why these conditions must be satisfied by an oscillator? That is what we are going to discuss now. The amplitude stabilization. So, initially the oscillator produces an output through the noise, and this oscillator basically has a positive feedback, and so the output will get regenerated. The output is increased instead. So, at one point the output will get sustained, and it produces a finite value of the finite magnitude. And if this A beta is not equal to 1 or less than 1, what will happen is the output will be reduced, the output will die out. So, this Barkhausen criteria must be followed by this oscillator. If the gain of the circuit is too high, it will saturate. If the gain of the circuit is too low, the oscillation will die out. Real circuits need some means of stabilizing the magnitude of the oscillation to cope up with the variability of the gain of the circuit. Why the gain of the circuit will get varied? Because of the temperature changes and the supply voltage changes. So, because of these factors, the gain will also get changed, and if the gain is high, the output will get saturated, and if the gain is too low, the oscillation will die out. So, we are going to see the types of oscillator. First one is RC phase shift oscillator. So, this is the circuit of RC phase shift oscillator. You can say this is an application of operational amplifier. So, this is operational amplifier, And what type of feedback is given? A negative feedback is given. Here the output is fed back to the negative input terminal, and feedback resistor is R2, input resistor is R1, third terminal is grounded, and this is called the feedback circuit. This is called the feedback circuit. In this circuit we have 3 RC pairs connected in series arm. The capacitors are connected alternatively, the resistors are connected in shunt arm. So, this is the circuit of RC phase shift oscillator. So, this is the feedback circuit and this is the amplifier circuit. We know that for the inverting amplifier, the input and output will get the phase difference 180 degree, and this feedback circuit must produce another 180 degree to satisfy the Borkhausen criteria. So, we are connecting 3 RC pairs. So, in practical, one RC pair will produce 60 degree phase shift. So, when you add the phase shift produced by these 3 RC networks, you will get 180 degree practically, but in ideal it is 270 degree. So, that is what we have discussed earlier. So, per RC network 60 degree phase shift will be produced, and if you add 3 RC networks, total phase shift is 180 degree, and this is the input output waveforms of an amplifier. So, we are going to derive the frequency of oscillation from the RC phase shift oscillator. So, for which we are taking only the feedback circuit of the oscillator, and we are considering all the capacitors are equal and all the resistors are equal. So, here C R C R C R, and this is the output of the amplifier, and this we can call it as the feedback signal to the amplifier. So, consider this current as I1, this current as I2, and this current as I3. So, now we are going to write the equations for each loop. So, this I1, if you take the first loop, I1 is flowing through the resistor R plus the capacitance 1 by Cs, and if you take this R, the resistance, I2 is also flowing. So, we are subtracting the current flowing through the resistance R, that is equal to V0, and here this loop R C R, if you take this middle circuit, the current flowing through this resistance R is I1. So, you have to subtract this I1 current from this resistance R, and I2 is flowing through these two resistors and this capacitor. So, I2 into 2R plus 1 by Cs. And what about this resistance? Through this resistance I3 is also flowing. So, subtract this I3 through the resistance R, and that is equal to 0. And the last loop, through this resistor I2 is flowing and there is no I1 current. You have to subtract the current flowing through the resistance R. And what about the current I3? It is flowing through two resistors and this capacitance. So, 2R plus 1 by Cs. So, when you put it in the determinant, it is 1 by RCS minus R. Here it is 0 and here it is minus R, 2R plus 1 by Cs, and here it is minus R, 0 minus R, and here it is 2R plus 1 by Cs. By the matrix you can calculate the feedback factor, that is beta. So, from this the determinant value of this particular matrix is derived as R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1 divided by C cube S cube. And from the circuit, what is I3? How will you calculate I3? You can calculate by calculating D3 divided by D. And what is D3? It is in this matrix, the basic matrix, if you substitute the third column by the voltage here, you will get determinant 3. So, it is RCS plus 1 by CS minus R V naught minus R 2 RCS plus 1 by CS 0 0 minus R 0. So, if you calculate the determinant value, you will be getting it is V naught R square. So, what is I3? By doing D3 by D, D3 is V naught R square. By D, you will be having R cube C cube S cube plus 6 R square C squared S square plus 5 R C S plus 1 divided by C cube S cube, it will become into numerator. So, this is I3. Now, after putting S is equal to j omega and assume that alpha is equal to 1 by omega RC, you will be getting the equation for beta is equal to 1 by 1 minus j 6 alpha minus 5 alpha squared plus j alpha cube. From this, if you equate the imaginary term, because beta has to be real, and so we are equating the imaginary term from this equation. So, you will be getting alpha into 6 minus alpha squared is equal to 0. So, alpha squared will be 6 and alpha is equal to root 6. And what is alpha? It is 1 by omega RC is equal to root 6. From here, if you put omega is equal to 2 pi f, the frequency of oscillation is given as 1 by 2 pi RC root 6. This is the frequency of oscillation of the RC phase shift network. And if this alpha value is substituted in this beta, you will be getting beta is equal to, if alpha is substituted in beta in the real part, you will be getting the value as 1 by minus 29. And we know that A beta, the magnitude of A beta must be greater than or equal to 1. So, if beta is minus 1 by 29, what is the value of A? It is greater than or equal to 29. And what is A? The gain of the amplifier. So, the gain of the amplifier from the circuit, it is A is equal to RF by R1. Modulus value is RF by R1. So, from this R, and this is equated to 29, and so RF is equal to 29 into R1. So, this is the value of the resistance we have to use in the amplifier circuit. So, these are the two important points. The frequency of oscillation of the sine wave oscillator is derived as 1 by 2 pi RC root 6, and the gain of the amplifier is derived as RF is equal to 29 R1. So, if at this particular frequency you are getting the sustained oscillation in the RC phase shift oscillator. We have a break now. Welcome back. This is a summary of RC phase shift oscillator. The frequency of oscillation is given as 1 by 2 pi RC root 6, and gain of the amplifier, that is the modulus of mod value of the gain of the amplifier is greater than or equal to 29. So, it is calculated as RF is equal to 29 R1. So, while designing the oscillator circuits, you have to see the values of the resistors such that the condition RF is equal to 29 Ri should be satisfied. This oscillator is used for generating the low frequency oscillation. And next is a Wien bridge oscillator. Why it is called as a Wien bridge oscillator is, we know that the bridge has 4 arms, and in each arm the Wien bridge has one of the arm, the Wien bridge has R, the resistance R, and another arm has also R, and in the third arm it has the series combination of R and C, and in the fourth arm the parallel combination of R and C is present for the Wien bridge oscillator. So, this oscillator has the name as Wien bridge. So, here what is the feedback given to the circuit? So, this amplifier, the feedback signal, actually the feedback circuit, the output of the feedback circuit is given to the positive terminal of the Wien bridge oscillator. So, this is the feedback circuit produced present here, and the output of the feedback is given to the positive terminal of the amplifier, and here it is always the feedback is given to the negative terminal for the amplifier. Here also the some output of the amplifier is given as input to the positive terminal. If you look at the circuit, only the 2 arms, the third and the fourth arm, it has, this is output. Here it is R1, R2, C1, C2. So, this is feedback, and totally from here it is output. So, what is beta now? It is Z2 by Z1 plus Z2. And what is Z2? Z2 is parallel combination of R2 C2. R2 into 1 by C2S divided by R2 plus 1 by C2S. So, it is R2 C2S divided by R2 C2S plus 1 by C2S. So, Z2 is R2 by R2 C2S plus 1, and what is Z1? It is the series combination of R1 C1. So, R1 plus 1 by C1S, it is R1 C1S plus 1 by C1S. So, if you put this Z1 Z2 in this beta, you will be getting, if you substitute those values Z1 and Z2 in the beta Z2 by Z1 plus Z2, you will be having R2 C1S divided by 1 plus R1 R2 C1 C2S plus S into R1 C1 plus R2 C2 plus R2 C1. And if you put S is equal to j omega, then beta will be equal to j omega R2 C1 by 1 plus j omega into the total term plus j omega into the total term will be coming. And we know that beta to be real, and the real term, if you take the real term equal to 0, it will be 1 minus, here it is S squared. So, you will be having minus omega square, since you have S squared in the beta term, and you will be having minus here j square, since j square is equal to minus 1, it is minus omega square, the total term, the total R1, R2, C1, C2. So, if you equate this real part to equal to 0, what is the value of omega square? It is 1 by R1 R2 C1 C2, and omega is equal to 2 pi f, and f, the frequency of oscillation, will be derived as 1 by 2 pi root of R1 R2 C1 C2, and this is the frequency of oscillation in the Wien bridge oscillator. At this frequency we will be having the sustained oscillation, and if you substitute this value in beta, that is, if you remove the real part from beta because it is equivalent to 0, you will be having only the imaginary term in beta. It is R2 C1. From here, if you assume that R1 is equal to R2 is equal to R3 and C1 is equal to C2, what is the value of beta? It is 1 by 3, and we know that A beta, the mod value of A beta must be greater than or equal to 1. If this beta is equal to 1 by 3, what is the value of A? The value of A must be greater than or equal to 3, and from the Wien bridge oscillator circuit we know that A is equal to 1 plus Rf by R1 because we have used positive feedback. So, A is equal to 1 plus Rf by R1, and this is equal to 3. So, Rf is equal to 2R1. So, this is the value of the resistance we have to follow for the designing of the Wien bridge oscillator. This oscillator is also used to produce audio frequency signals. So, these are the 2 points we have derived from the Wien bridge oscillator. What is the frequency of oscillation? It is f is equal to 1 by 2 pi RC, and what is the gain of the amplifier? It is A is equal to 3, and if it is 3, then what is the value of Rf and Ri? It is Rf is equal to 2Ri. Suppose if the question is design a Wien bridge oscillator for the frequency 1 kilohertz. So, you have to design, you have to take this frequency as 1 kilohertz, assume, you have to assume the value of C capacitance as less than 1 microfarad and calculate the value of R, and here also you have to assume the resistance Ri as 10 kilo ohms, and based on this condition you have to calculate the value of the resistance. And now next is triangular waveform generator, and this triangular waveform generator can be implemented by cascading 2 applications of operational amplifier. Can you recall the circuit of the A-stable multivibrator? What is the output of A-stable multivibrator? The operational amplifier is used as a comparator in A-stable multivibrator, and we know that the comparator outputs plus or minus V saturation always based on the magnitude of the signals present at the negative and the positive terminal. So, the A-stable multivibrator without any input signal, it is producing a square wave output. So, this square wave is given as the input of an integrator. This integrator will convert the square wave into a triangular waveform. So, this is a simple application of operational amplifier. So, either you can use A-stable multivibrator as a first stage, or you can use a skimmer trigger. Skimmer trigger is another application of op amp in a comparator mode or open loop mode. So, skimmer trigger, we know that skimmer trigger has a positive feedback, and to the negative terminal we are giving input signal, and positive terminal we are giving a, say this is R1, this is R2, and here an integrator circuit. That is all. This is producing a square wave skimmer trigger, and if the square wave is given to the integrator, this is going to produce a triangular wave. This is another application of operational amplifier as a triangular waveform generator. To summarize this lecture, we have seen a sine wave oscillator in which RC phase shift oscillator and Wien bridge oscillator, both the oscillators are used to generate low frequency signals, that is audio range of frequency signals, and we have derived the frequency of oscillation for both the oscillators and what is the condition to be satisfied for the gain of the amplifier, so that A beta must be equal to 1. This is one of the condition of Barkhausen criteria. And next is triangular waveform generator. This was implemented by two different circuits. One is a stable multivibrator cascaded with the integrator, and another one Schmitt trigger cascaded with an integrator. A stable or a Schmitt trigger circuit which produces square waveform, and if the square waveform is given as input to the integrator, it will produce a triangular waveform. Some of the questions here: what is an oscillator? List the types of oscillator. What is Barkhausen criteria? And how the triangular waveforms are generated. References. Thank you.